Aaron, your humming is live.
My humming is live.
Your humming is live.
Okay, there we go. Oh, that's such a beautiful image.
It's really gorgeous, isn't it? Hello to everyone who has already hopped on and is watching. Just letting you know that we will get started in just a few minutes here. We tend to give a couple minutes at the beginning of the stream to let everyone trickle in so that we're starting the talk with the full contingent of people that we will be presenting to. So we'll be with you in just a couple minutes.
Okay, there we go.
I think when we hit the 4, we'll start.
Yeah. The beginning of these streams are just so riveting.
Really incredibly sad one. We've got a gorgeous picture there. We've got the loading title. We've got the two of us awkwardly trying to make noise or trying not to make noise. Now we're making awkward small talk, which is even better.
What? It's more entertaining this way, I think.
That's absolutely true. All right, I think that we ought to get started here. So, hello everyone. My name is Alexander Criswell, and my co-presenter today is Aaron West. We are going to be talking to you today about cosmic rays and the aurora, two types of precipitation the weather forecasters don't talk about. I'll just give a little bit of an introduction for myself. Again, like I said, my name is Alexander. I am a graduate student at the University of Minnesota. I study gravitational waves, which is quite far removed from the topic today, but the real expert here on this sort of thing is my co-presenter.
Oh, that's a dangerous introduction. Hi, my name is Aaron West. I'm a graduate student working on my PhD at the University of Minnesota, and I'm trying to understand how aurora happen and different acceleration mechanisms, which is something I'll talk about later, actually, in this presentation, and hopefully you'll understand it after I've talked about it. I think without further ado, let's get going. So, precipitation you may have already heard of are things that we associate with weather: rain, snow, sleet, especially snow in Minnesota. But precipitation you may not have heard of, things which precipitate out or fall out in our atmosphere are things like aurora or cosmic rays. So I'll be talking about what aurora are and how they happen. And then after I've finished that, Alexander will take over cosmic rays. So next slide. So I just wanted to bait the hook a little bit with some more beautiful images of aurora. This shows aurora borealis and australis because we have north and southern lights. And this shows the breadth of color and structure. And I don't know, I really love these images, and I hope this gets you excited for what we're going to see today. So where do we really start with this? We start by remembering that the sun is a gigantic magnet and that space is not empty. We think of both of these things in a fairly simplistic way, but the sun has a lot of very unique features to it. And the first thing I want you to think of is the sun is a ball of plasma which contains a bunch of magnetic fields. Plasma is a fourth state of matter where electrons and ions break apart, so they cannot recombine. It's usually very hot. And because both electrons and ions are charged particles, they follow magnetic and electric fields. Think of it this way. If you have a fridge magnet, and if you have a ball of plasma here, the magnetic field lines will embed inside the plasma. And if you move the fridge magnet around, the plasma will follow. Same if you hold onto the plasma, the fridge magnet will follow where you move the plasma. So we have the sun as a gigantic ball of magnetized plasma, and it's burning off constantly. It's on fire. That leads to a solar wind flowing out from the sun, carrying this magnetized plasma, and that impacts Earth. As a fun little factoid, that solar wind is flowing out typically at a speed of 400 kilometers a second, or in something you interact with every day, 1,000,000 miles per hour. It's extremely fast. Now, that solar wind carrying all of that plasma impacts Earth, but not quite, because Earth has a force field to hold back that wind. And that force field is Earth's magnetic dipole. We have a core inside of the Earth, which is a dynamo that creates a magnetic field around it. And as I've said before, if you have a magnetic field, the plasma will follow it. So if you're forcing plasma into a magnetic field, it's going to flow along these arrows you can see on the screen. So these arrows flow into, and if you reverse the sign, I guess, into the north and south poles. Basically, the plasma is going to latch onto one of these lines, and it's going to follow all the way down into the Arctic Circle or Antarctica. And that alignment of plasma and that alignment of electrons and ions into our atmosphere is what gives us aurora. So what is aurora in actuality, huh? Well, when we have electrons and ions, but I'm going to focus on electrons for this explanation. When we have electrons coming into our atmosphere, they're going to hit molecules that are suspended in our atmosphere, floating around, typically in a gas. Sometimes they're ionized. When the electrons hit some of these molecules, those molecules become excited. They have a bunch of energy bound up inside of them, and they're waiting to get rid of that energy somehow. And one way they can get rid of that energy beyond just vibrating a lot is actually to give off light and emit different colors of light based on the frequency that correlates to the energy that they need to get rid of. So we have electrons coming in, impacting molecules. Molecules get excited, molecules cool off and create light. But that's not the end of the story. We also have layers of precipitation. We have a kind of an altitude gradation of where you're going to find different impacts of electrons and ion species. For instance, very high in the altitude, an electron can impact an oxygen ion, and that oxygen ion can emit red light. If we go a bit lower, we have a chain of an electron hitting a nitrogen ion and then re-emitting to hit an oxygen ion with a different energy than it came in with, and that'll give out a green light instead of red. And then even lower below that, we have usually a bit fainter in color, electron hitting molecular nitrogen, two nitrogens bonded together, and that will emit a different color of light called purple or lavender. It depends on what palette you want to use. So that talks about what aurora look like and the driver behind it. But what about all the different structure? Where's that coming from? Well, there are a lot of different ways we can talk about what aurora look like from the ground. And we can talk about how things look like glow, bands, folds, etc. But I want you to think about three very important factors for what observing the aurora on Earth's surface is like. The first thing that you see from a bunch of images, and we'll see in images later in the talk, are observation time. If you have a camera that has a longer exposure time, you'll be able to make the aurora brighter because you're taking in more light, but you also smear out more of the structures that you would otherwise pick up. Second one is observation angle. If you are directly underneath these precipitating electrons, it's going to look like a corona or something. It's just like a crown of light above you. If you're far off from a different direction, you might see these more as ribbons or just stacked on top of each other as a single band across the sky. Finally, the driving process, although the solar wind is the ultimate driver behind a lot of this energy that's being put into our atmosphere, that can filter through different sources in Earth's magnetic field, and that can vary in shape and size locally, which is why, at least in the background behind my my image, you can see all of these different evolving images, right? It's not just a flat illumination, there's a lot of structure, and we're going to take a look at some of it. First off, this is kind of looking at the horizon. This is what I would mostly term auroral glow. You can't really see structure here, but you can see the very definite nitrogen to oxygen emission in the green emission band. Staying in the same place and moving forward in time, we can see that this aurora moves closer to where we are, and we can begin to see the differences between bands of these excited molecules, giving us these different structures. And if we advance a little bit more, we look over to the other side, we can see there's a bit of a swoop to it. There's definitely some structure here, but we're looking through a bunch of them at the same time, so we can't really see a lot of the extra small scale structure. If we wait a bit longer, it begins to move out over us, and we see these folds develop, and we see these vertical lines, and these vertical rays are because you have electrons coming down field lines, and electrons coming down field lines will sometimes group and will sometimes leave areas that are void of electrons. And over time, you'll have things moving from side to side, switching from one channel flowing down to one channel flowing upwards, and you'll get gaps in between auroral bands. This is just going to be a really quick aside. This is something we've looked at more recently. It's not actually Aurora. It's called Steve. I can go into this more later, but I wanted to bring it up as it's more recent. It looks really cool, and it's another example of what plasma physics in our atmosphere can do, even if it's not directly related to the solar wind. Now, we are not unique at Earth in having aurora. We have aurora at other planets too in our solar system, and we assume in other systems outside of ours at other exoplanets. Jupiter and Saturn in particular have very strong magnetic fields, and because they have strong magnetic fields, the emission lines for their aurora are in higher frequency bands than the visible light. Saturn's aurora appears in ultraviolet, and Jupiter's even extends from ultraviolet into X-rays. Not something you want to see up close. Not that you could withstand the gravity. Finally, I want to close with why do we really care? Aurora are beautiful and very interesting, but I mean, at least one way to justify researching this is space weather. You may have noticed precipitation is used for weather at the very beginning of the talk. Well, that's not a coincidence. The solar wind as well, all of it feeds together into a system that the NOAA Space Weather Prediction Center, you can see down at the bottom of the screen, uses to try and predict what space weather effects we will see on the planet. So aurora are basically a way of telling us if we're having magnetic storms from something happening on the sun or something happening in Earth's magnetosphere, and telling us what that's going to do to Earth's electrical systems. Geomagnetic storms on Earth can hold hundreds or more of gigawatts, and they can induce ground currents that can short out power stations, transmission lines, and cause other havoc. And I'm about out of time, so I'm going to finish up by saying in 1859, we had something called the Carrington event. Earth was hit with an extremely strong wind from the sun, and that caused visible aurora instead of up at the polar cap, all the way down at Hawaii and Cuba. Now, if you think about this, in 1859, we didn't have the level of technology we do today. If we experience another Carrington type event today, we want to know about it in advance so we can prepare. But also, aurora are beautiful.
All right. And with that, we are going to move over to start talking about the other sort of precipitation that we've promised this talk will be about tonight, which is cosmic rays. Now, cosmic rays are not Ray Charles or Ray Bradbury. They are actually not rays at all. They are misnamed as cosmic rays because when we first started seeing them, astronomers didn't know what they were exactly. But it turns out that they are actually super fast, really high energetic charged particles, things like protons or helium nuclei that have had all of their electrons stripped away from them. They are nigh on relativistic, and they come from a wide variety of sources, and we're going to talk a little bit about that. So, like I said, the main two types of cosmic rays, really a cosmic ray refers to any sort of extraterrestrial particle that is charged that comes flying in. The two most common types are protons and alpha particles, which are those helium nuclei that I mentioned earlier. A lot of these names you'll notice were come up with by folks who didn't really know what they were looking at and just said, okay, we've made this new sort of particle detection. I'm going to call it an alpha particle. This is a talk about precipitation, so I had better talk about how these things are precipitating. And it turns out that as cosmic rays, a proton or an alpha particle, hit the molecules in the upper atmosphere, it actually causes a cascade or a rain, if you will, of other particles to go down through the sky, turning into a wide variety of particles as they cascade downward. A really interesting fact about this is one of our best early proofs for special relativity, because some of the products of these cascades couldn't actually ever reach the ground if time wasn't moving slower for them because they were moving so fast. These cosmic rays come from a variety of sources. The main one is the sun, mostly by virtue of the fact that it is very close. And so those streams of charged particles that Aaron was talking about are actually in and of themselves, some of them are cosmic rays. And if they're going fast enough, they cause this exact sort of behavior that I'm talking about with the precipitation and the cascade of other particles coming down through the atmosphere. On the other hand, it can also come from more exotic and far away sources. Things like active galactic nuclei, where a supermassive black hole at the center of a galaxy is swirling material around it and ejecting it from the galaxy in these gigantic jets that are going so fast that eventually these particles do actually reach Earth, and we can detect them. And then another thing that we see cosmic rays are these explosions of stars at the end of their lives called supernovae. The supernovae version of cosmic rays are actually suspected to be the cause of the Pliocene extinction. Because the Earth about 2.5 million years ago was bombarded by so many cosmic rays that the radioactive, fallout basically, affected disproportionately megafauna, and so all of the really large animals died out. So this is weather. What's the forecast? Some of the cool things that we found while we were looking through and kind of researching this topic is that processors, like in your computer, actually have to take this into account. When a cosmic ray strikes your computer at the rate of about 1 error per 256 megabytes of RAM per month, it will flip a bit on your computer and change the value from a 0 to a 1 just because the energy of the cosmic ray hitting the electrons that are storing those states in your computer. And in the future, microprocessors are going to be so dense that this will become an actual problem. And so Intel is working on built-in cosmic ray detectors to sense when a cosmic ray has hit the processor and deal with the error before it becomes a problem. And there is also a very cool solar orbiter mission that is coming up. It doesn't look like we quite have the time to elaborate on that, but you can feel free to look into that if you so desire. And that is the end of the talk portion of this show. So if you have any questions about the aurorae or cosmic rays, please put them in the chat. We've got probably about 5 minutes to answer your questions on this, and then we're going to move over to a panel discussion of who astronomers are, and what we do and kind of the lives that we lead as people, and not just the scientists, or not just the science that we're creating. So we'll be taking questions from the public for that as well. So if you have any burning questions about who astronomers are and what we do, we have a whole bunch of really cool astronomers to answer those. So we did have a good question that I saw in the chat while Aaron was talking, and I promised to get it answered. So from Olivia, is it possible to recreate an aurora in a lab, Aaron?
So, yes. If you want to think of aurora as the emission we get from electrons hitting dispersed ions, yes, we can do something like that in a lab. If you work in a bit of a vacuum, the light emitted is not going to be huge. But if you want to do plasma stuff at home, you can also create plasma at home. Every time you light a candle, technically that candle flame is composed of some dissociated electrons and ions. So that's another way of looking at what a plasma can be in the comfort of your own home. Still, it's fire, so be careful.
We've got another question here from Martin, which is, where on Earth are the best places to see the auroras? And does it matter the time of year that you go?
So, the best places to see aurora, it's difficult to see the aurora australis based on how close to the South Pole you would need to be in order to actually recognize it, and the population centers around there are kind of sparse. But The better places to be would be up in Canada, up in some parts of the EU. The farther north you get and the clearer skies you can find, the more likely you are to see it. More impactful on whether or not you will see aurora is the activity of the sun. If the sun is quiet and it's not pushing out strong solar wind, we're not going to see very strong aurora. We might see a little bit, but as the sun winds its way back up towards solar maximum, we'll be able to see more aurora.
Just as kind of an add-on to that, we have Nick in the chat that has asked if there's a particular time of night or day that is better for seeing aurora.
Well, if it's daytime, it's going to be very difficult to see the aurora. It's not a super bright phenomena outside of Carrington event type magnetic field strengths, but generally we're looking at midnight, times when you don't need to deal with any even horizon glow from the sun that might pollute the air and and make it more difficult to see the contrast of the aurora on the night sky.
And I think we probably have time for just one more question, and I'm going to pull that from Rod, who asks, are the Van Allen radiation belts would capture the charged particles? And is it true that they're worried about the Apollo astronauts going through these belts?
So the Van Allen radiation belts are a phenomena because we have this dipole field around Earth. There are pockets where these charged particles, this plasma, can get trapped, and it can build up with some pretty significant energy. And those radiation belts, so termed, were termed that way because early satellite readings from it tripped off the radiation detectors because they had a bunch of charged particles hitting it. It's not radiation in the same way like you would get gamma radiation, but yes. So some of the charged particles flowing from the sun will get trapped in the radiation belts. Some will be transient and actually sweep through the Earth's magnetosphere and then go out the back end. Others will propagate down the magnetic field lines to impact on Earth. It's kind of an apportionment issue. But yes, the radiation belts are important, and there is a lot of really interesting research on how the radiation belts impact and function with aurora.
Hey, thank you, Aaron. There are a number of excellent other questions in the chat that unfortunately we're not going to have time right now to talk through. Although, Aaron, as you are pulling questions from the chat about who we are as astronomers, feel free, if you have time, to answer some of those, as I feel like you'll be fairly well equipped for them. With that said, we are going to move over to the panel part of this discussion. And so let me just get that pulled up and move into gallery view here as I welcome our panelists. Hello, everyone. Thank you again for volunteering your time to do this. Hello, Evan. Good to see you. I'm glad you could make it on. So what we're going to start off by doing is just going around the virtual table, so to speak, and having everyone introduce themselves, just telling us who they are, what position they hold, and the brief 5-10 second version of what their research is. So let's get started with Bob Gers here. Bob, you are muted.
Hello, I'm Bob Geertz. I'm a professor in the Minnesota Institute for Astrophysics. I hold 2 degrees in physics, a Bachelor of Arts and a PhD. I build instrumentation to primarily look at infrared radiation I've helped NASA build a bunch of observatories. I built the world's largest infrared telescope in Wyoming in 1972. It's not the biggest anymore. And I observed with this equipment in the telescopes that I built. And I especially like to observe transient events like nova and supernova explosions.
Fantastic, thank you. Evan, if you could introduce yourself next.
Okay, it looks like we're going by age.
We are going by the right to left order of my screen.
Okay.
It's descending age we're going by.
I'm Evan Skillman. I've been at the University of Minnesota for 30 years now. I work primarily on extragalactic astronomy, observational extragalactic astronomy, and concentrating on nearby galaxies, and mostly the little ones, what we call the dwarf galaxies.
Right, fantastic. And just to prove that I'm not actually going down by age, Lauren, not to imply that you're older than Evan, you get the joke when I introduce the next person. Anyway, please talk, saving for myself.
Hey, I'm Lauren Loftman. I am a second year grad student at Minnesota, and I study green pea galaxies with Claudia Scarlata. Green pea galaxies are called that because they're small and green and kind of roundish, and they're pretty cool. I think that's all right.
I think that sounds good to me. And now, so that everyone gets the joke, we're going to go to the other Bob here.
Hi, I'm Bob Lysak. I'm actually 1 month older than Evan, so but I'm a professor of physics here at the University of Minnesota, and also associated with the Minnesota Institute for Astrophysics, as we all are. And I study the aurora. I'm been done a lot of work on the role of the Earth's magnetic field and how it can accelerate the particles that hit all those atoms that Aaron was talking about, and Aaron is actually working with me towards his PhD. So I'll have to correct all the things he said earlier. Then.
All right, thank you. Having talked to someone that Aaron works with, you now get somebody that I work with. And Sharon, if you could introduce yourself.
Hello, everyone. I'm Sharon Banagiri. I'm a PhD student at the School of Physics and Astronomy. I'm originally from India, and I work on gravitational waves. You might have heard about it recently, and I work on the LIGO experiment.
All right, thank you. And Nico, if we could get your introduction next.
Hi, I work at the Minnesota Institute for Astrophysics, just to show off that I'm also wearing a relevant shirt. I got my degree in physics a few years ago, and I'm now on my third year going into my third year of a PhD program like Lauren, Alexander, and Aaron. And I study what is known as clumpy galaxies, which are just a very friendly way of saying galaxies that have small spots for galaxies of very high star formation. So they're a special type of galaxy that I'm looking into.
Thank you, Nico. And now, last but most certainly not least, Lindsay.
Hi, I'm Lindsay Gleasoner. I'm an assistant professor in the School of Physics and Astronomy, and I wanted to joke that I'm 1 month older than Bob Lysak, but I have the feeling that people probably wouldn't believe that if I tried. I am a high-energy solar astrophysicist, so let me break that down. You know what an astrophysicist is, or you'll get an impression of that throughout the evening. Solar means that the astrophysics that I'm interested in happens on the sun, and high energy means I mainly use things like X-rays and gamma rays for my observations. I make observations of the sun in X-rays and gamma rays, and I also work a lot on instrumentation. And a lot of my instruments fly on things like CubeSats and small sounding rockets.
Hey, fantastic. Thank you very much, Lindsay. So to everyone out there watching, again, please, this is primarily a session for you to satisfy your curiosity about the people that do the astronomy that you've heard so much about. So please put questions in the chat if there are things that you've always wanted to ask an astrophysicist, or if you're just wondering something about who we are as people, feel free to ask. We will get started. I have a couple of questions prepared while you put yours in the chat. And so something that I would actually like to know is, what is something that you folks do that has absolutely nothing to do with astronomy whatsoever that you still think is really cool and important? Because ultimately, we are just regular people, even though we do this job and stare up at space a lot. So anyone that has something that's popping to mind immediately, feel free to go ahead and talk about it.
Well, I'll pop in there. I still, at my age of 75, love to play ice hockey and do about 50 plus games a year. And in my spare time with my wife, we build model trains and go kayaking and all sorts of things.
I know you're all
I'll
very
mention
interested.
that what I spend a lot of time on, or a lot of time with outside of work, is generally this little guy. My son is 16 months now, so he just started walking a little while ago, and that's really what I spend a lot of my off time doing. It's a lot of fun.
Well, I'm a happy person right now because I'm a big baseball fan. That's one of my big things. So I'm really glad to see the game starting up again, and I'm also interested in hiking and bicycle riding and reading. A lot of science fiction and history are my favorites.
Not something I can do right now, but one of my goals is to go storm chasing and see tornadoes and stuff eventually. Kind of limited this summer because traveling is not a good idea. But next summer, I promise I'll come back with photos of tornadoes for you all.
Okay, we've got one question here. This question is from Anna, who is 7, and she asks, "Are astrophysicists worried about space junk?"
Ooh, Lauren, you want to
Yes,
take this
we
one?
are. Yes, it's bad. And I just also like to categorize Starlink as junk up in space. So I think that's also space junk, just to put that out there before anyone can stop me.
That's the Starlink satellite system, and just to put in a second for that, we are worried about it as astronomers. It's not just Lauren; that is many of us.
So what makes you particularly passionate and concerned about space junk, Lauren?
It gets in the way. Like, how are we supposed to go and travel and put things in space when there's all this little stuff out there from broken down and whatever satellites that could at any given moment crash into our own satellites? And if we can't track all of it, then our own satellites are toast. Everything we put up there is toast, and then it crashes and creates more debris and more toast. You know what? Toast could be up there too, honestly. No, just kidding.
There's
There's
another big concern too, and that is that some of the communication systems that are planned for stationary Earth orbit will create enough light pollution that we'll have trouble seeing some faint objects in certain directions in space.
Mm-hmm. There have been studies showing that, like, at a given, once the full Starlink constellation is up, the constellation of all the Starlink satellites, then we won't be there'll at least be a satellite crossing an image taken from LSST, an important telescope. Like almost every image taken in the evening, where you'd normally get like twilight images, will be literally ruined. And not just Starlink, but other space junk too. When there's enough up there and it's reflecting back, it is not good.
I'd just like to add to that to see early evidence of this, one of the photos that you can look up is that Lowell Observatory was taking an exposure of space, and this was just after the Starlink satellites had started to launch. The reason that Starlink satellites are problematic is that there are just more of them than there are other types of satellites, or just satellites in general, that have been in orbit around the Earth in the past. So all of a sudden, our satellite count is going up by many, many, many times in this very quick succession. So what this team discovered is that after a batch of Starlink satellites had been launched, they had all of these streaks across their images that basically saturated some of the pixels that they were hoping to analyze. And so this very careful image that they had spent a long time and a lot of effort trying to take was basically ruined, because there were these objects flying across the camera that were reflecting light from the sun back onto the telescope. So that is the issue that we're concerned about as astronomers specifically, is that a lot of the things that we do on the ground will be sort of impeded or made impossible in some cases if the satellite count around us gets too high.
And it's not just like professional astronomers either. Even amateur astronomers have trouble with this. Like I've seen multiple photos of people trying to take long exposure shots of neowise, having their photos being ruined by Starlink.
I'm going to jump off of that. We just got a question about that particular topic. What is that new comet in the news, and why is it important? Anyone who wants to jump in on that? Evan, you're muted, by the way.
I was just going to say Bob is an expert in comets, so he should probably answer that question.
And say it again in detail.
So the new Neowise comet that's been in the news, what's special about it, and why are we telling people to go out and look at it?
Well, it's very bright. It's seldom that you get a comet that's bright enough to see by naked eye, even in the evening. So this one is coming especially close to Earth. And one of the tragic things about this is it's one of the best opportunities to look at a comet in the infrared and at other wavelengths from observatories on the ground, and we aren't able to do it because of COVID. I have an observatory that I run on Mount Lemmon in Arizona, and the Arizona people will not let us go up to that telescope to do anything unless we go up one at a time and unless we quarantine for 14 days upon arriving in Arizona before we can go up to the mountain site where that telescope is. So we're basically out of business professionally on this particular comet, except for observations from some satellites.
Okay, I've got another question here. Is it possible to combine my love of animals, space, and physics together into some sort of future career?
Well, I will say that the field of astrobiology does exist. I don't know if there's anyone here that knows a fair bit about it.
You can also have a pet.
There is that.
I have an idea of a career to go into for this.
Please.
I think that you should go into a career of naming missions. People always have to come up with cool names for their missions, and it's usually some sort of acronym, but that acronym needs to stand for something related to the science. So you need to understand the science of what it's doing too. And if you can have an animal as your acronym, then you get to have an animal as your mascot, your logo.
Tell them about your acronym.
My project is called Foxy. And we have fantastic logos. But I'm sort of kidding about this being a career because there's not one person who decides these, but it is a highly coveted skill because coming up with a good name for your project is really important.
Another example that's actually perhaps more geophysical than astrophysical, because actually some of us that study the Aurora work at the American Geophysical Union. That's our main meeting. But there's a lot of people working in what are now called biogeosciences. So the interaction of living beings with the geological environment, and that I think is a growing field, and so that would be something to think about if you're interested in those things.
I'm going to throw out one more thing before we move on to a different question. We found that certain birds actually use Earth's magnetic field to migrate. And in cases where the magnetic field of Earth is significantly impacted by the solar wind or some other effect, birds can get lost. Homing pigeons in particular are a significant driver of that research.
Can I add one other thing to that question? If you are willing to go into space and be an astronaut, there are people who do biological experiments on the International Space Station. And as we think about establishing habitations on the moon or on other planets, I think that scale of experiments will increase. So that might be also a fun way to go.
And to cap that off, Martin in chat also mentions that going into career programs such as renewable energy or environmental engineering are a great way to tie that knot and bring all that home together. A new question that came in, which is, I think, very apt to this panel. What is your daily work life like as an astronomer or astrophysicist? Perhaps not directly impacted by COVID, but like in a normal year.
I would love to hear answers for this question from folks at different spots in their careers. So we could get one of the grad students and one of the more senior professors and one of the earlier career professors. That would be fantastic.
I would like to take off on this really quickly because this is part of why I was excited to have a panel for one of these events, is that we are very qualified to talk about what research scientists do. And what research scientists do in astronomy is I think, very different from what most people imagine astronomy to be like. Even going into this PhD program, I imagine there would be more people, just by count, who were at least familiar with telescopes. Like maybe who had one, or like who went to one regularly and like took actual data. I have never and will never visit a telescope to do research or to take data.
Okay,
Lindsay's
but you're not
wrong over in the corner.
I'm just going to mention you're not an observational astronomer, Nico. You don't count. No, I'm just kidding.
I'm not. So there are people who are observational astronomers who would who this is not true for. But just by total count, astronomy as a field is a lot about sort of sitting in an office and thinking very hard about space and trying to make sense of the data that other people have taken. So it is worth thinking about as people chime in with what they do.
So
from my point of view, I mean, a lot of the work that I do is computer modeling of the Earth's magnetic field and the acceleration of auroral particles. This has the advantage that, you know, with the internet these days, I can do this from home. So that part of my my work is really not impeded very much by the coronavirus. But of course, the other side of it is talking to people and spending time on Zoom, which is something that we've all become very familiar with. So this is all a big part of our day in the present era.
John, you were starting to say something?
Yeah, so similar to what Bob said, a large part of my work involves sitting at a computer, looking at data and trying to write code to understand what the data is telling us. But before COVID, in the before times, I would sometimes visit one of the LIGO observatories and spend a few months there to work on electronics or work on noise suppression and things like that. So that's more hands-on work, but most of the work I do can be done just by sitting at a computer.
I'd like to add that, like, when you picture an astronomer, as Nico said, like most of them, you aren't just trekking out to your telescope in the middle of the night on a hill looking like your picture of Galileo or whoever, but a fair number of astronomers like do actually, like, we get our data, a lot of it nowadays is remote from like these telescopes, but observational astronomers, as a treat, you sometimes get to go to an observing run, and you're out there and you're up all night drinking a lot of coffee or tea or whatever is your cup of tea. That didn't work right. And you stay up all night and you do get the data, and then you come home and spend the next several weeks at your computer trying to get your code to work to reduce the data to a usable form. So yes, in all fairness, a lot of it is spent trying to get your data to work and then analyzing it with code. But like, astronomers still do get to go and collect some data, and it's actually really fun because you get to like travel the world and see all these cool giant telescopes. Like, it's really an experience to walk into a room and see that the mirror of this telescope is larger than your car. Like, it's really something else.
I'd like to hear from Lindsay as well on this. I think we can get some good insight.
Yes.
Yeah, in fact, I'll piggyback off of what Lauren said, because she mentioned that there are parts of the job sometimes that involve going places and doing things. And I think what day-to-day life is like was a powerful motivator for me in choosing the type of astrophysics that I wanted to go into. I mentioned that I do some work with instrumentation as well as observation. And that means that I get to spend some time in the lab working on actually building instruments, or increasingly these days working with other people on building instruments. And that to me, like I said, was a powerful motivator, because it means that I do spend a lot of time with a computer and in meetings. That's something every astrophysicist does. But I also get to get into the lab and get my hands on some hardware. I actually feel like I'm constructing something with my own hands, with carefully gloved hands and cleanliness, of course. And then we do, at a given point, take those instruments somewhere and actually fly them. And so as part of one of the experiments that I work on, we actually take the telescope out to a launch facility where it flies on a sounding rocket. And we usually spend something like a couple months out there total for the launch campaign. And most of that is getting ready for the actual launch and flight of the thing. The flight itself is over in 15 minutes. And so kind of like Lauren said, it's a lot of work to prepare for things like that. And then we spend years afterwards analyzing the data.
I think something that surprises everyone who's not an astronomer is the amount of time we spend writing proposals. To get time on the Hubble Space Telescope, for example, it's almost all peer reviewed, and the oversubscription rate is usually around 8-1. So we need to write several proposals to be successful with a single one.
Evan, could you explain what an oversubscription rate is?
That there's requested by in a annual proposal cycle, there's 8 to 10 times more observing time proposed for than is available. There's finite amount of time on that telescope. And so I was going to continue on with Lindsay needs to write proposals to get things to build the stuff that she builds. Bob Lysak just got a large grant to support Aaron, I expect in the future, or other people that he's working with. And Bob Gerritz is getting ready to submit proposals for the James Webb Telescope, which is coming up in just a few months. So it's a sort of invisible part of the process, but it's what we all spend a lot of time on. It's the most competitive part of the process, actually. And so it requires a lot of attention and a lot of skill just for proposal writing.
Yeah,
Go ahead, Bob.
Oh, I could chime in on a few of the other things that are associated with being a research astrophysicist who's also a research professor. So I teach half-time during the school year. I'll teach 4 hours in the class during the week, and it probably takes me twice as much time out of class to prepare lectures. And I spend a lot of time supervising the research of undergraduates and graduate students in my lab. Spend a lot of time, and the rest of the time is spent in my lab, building and testing equipment, going out to the telescope, observing, and then taking the data and trying to develop theories based on elementary and fundamental physics to explain what I've been observing. And I have to write that up into papers, and I have collaborators all over the world I'm working with on this. We get together in person sometimes, and now weekly on Zoom. And I've been able to travel all over the world to do research with these people. I've taken 80 trips to foreign countries between 1985 when I came here and now. And now my traveling is curtailed, of course.
All right, I think that has been some excellent discussion. Aaron, do you have another? I'm seeing a couple great questions coming in through the chat. Do you have another one for
I've
us?
got one in particular for the women on this panel. What has been your experience in the field, and do you see more women pursuing this avenue of science?
Lindsay, do you want to talk first, or should I?
Sure, yeah. There's never really a quick answer to that question. I would say that there have been some challenges. Women are not well represented in this field yet, though I think we have seen a lot of evidence of that changing not as quickly as it needs to. I think issues like implicit bias and sexism are present in our field as they are in pretty much all fields. I have dealt with that occasionally. And it's something that the field as a whole continues to struggle with, but I think is also making quite a bit of good progress on. Lauren, what's your perceptions? I'd love to hear what you think about that.
So like, I will admit, like when I was applying to grad schools and I was looking at the department, and I'm like, it was a hard decision because like everything about here, like at Minnesota, was like, oh wow, I really love the culture and stuff, and I was like, aha, oh no women, okay, well, okay, there's one, but I still came here, and we're actually improving. Like there were several in my year and stuff, but it's still difficult, especially as like a queer woman, to like go into a place or a field where there's like no other representation and feel like, do I have to forge a path here? Like it's not isolating per se, because like I still have lots of friends and stuff, but it's how do I describe it? It's an adventure. Good one. I have lots of support, but it's still just like I wish there were more of me, I suppose. But
We
yeah,
wish that
like
too.
this year, like in my year, there were like sorry, Alexander. Besides, Alexander was the only guy in our year. And then like this coming year, it's kind of like an even split for the new upcoming first years. And so like we're improving, but it's always a question of how do we recruit more women into our department? How do we convince people on visit weekends that, hey, we're great, you should come join us and stuff? Like, how did our year even end up so diverse when we all took a look and saw, there's not as much diversity here as I'd like? It's an interesting question to go into. Not to shade the department or anything, I swear, but like, yeah.
All right, I have one ending question for the entire panel. I think this is a fun question to end on. What is something you wish you could do just to be able to do it? Short answer, first thing that comes to mind. I'll answer first, just to get it out of the way. If I could have telekinesis, I would do it. I don't really care how. If I had the ability to move things with my mind, I would do that.
I would love to have a supernova go off nearby. Not nearby
Not
enough
too
to harm
nearby.
us, but near enough to get some really good data on.
Of course, I grew up in the 60s in the middle of the space race, and one of the things I always wanted to do was to go into space. And well, I think I'm probably too old to achieve that at this point, but I think studying space science and astronomy is the next best thing.
I'm going to throw in a
So,
completely
go
I'm
ahead.
going to throw in a complete non sequitur answer, which is that I'd like to be able to play guitar, and I'm currently working on that dream. So
Good prop.
Sure.
So since superpowers look like an acceptable answer, I'm gonna say I would like total control over the electromagnetic force. That would be like Magneto, but Magneto is vastly undersold in the movies and the comics. Like he should be able to do a lot more than he can do. But a more serious answer is, yeah, probably a supernova, provided that the LIGO observatories are running at the time. That would be awesome. Lots of data, spectacular calibration for measuring Hubble constant, and yeah, that would be the first time we would ever see that in gravitational waves, and who knows what we would learn.
I think for me, like, I would honestly just say like teleportation, but for the reason that I just really, this sounds really bad when I say I really like natural disasters, but I really want to like see tornadoes and lava and lightning and stuff up close. And so if I could teleport, that would be really convenient instead of having to like drive or fly everywhere to get to these natural disasters. And it would make it easier to get out of danger really fast.
a much easier way to get to space.
Oh, that's a good point too, actually. Yeah, that too. I could teleport to the ISS.
And Evan?
Oh, I feel very inferior in this regard. There's a couple people I'd like to see in concert. Jonas Kaufman in an opera and Mitsuko Ikeda on playing anything by Mozart. But this is the control of all forces sounds pretty cool.
All right, and I guess, Lindsay, did we get to you?
No, let's see. Bob Lysak stole my answer because the thing that came to mind first was go to space. But I do have a second answer, which is I would really like to be able to learn languages easily and be fluent in a lot of languages. That just feels like something that is so hard to do and almost feels out of reach. I would just really love to be able to do that.
Yeah, bull.
And I think that then leaves me, and I've been sitting here the entire time torn between two, so I'm just gonna say them both. So on one hand, on like the space side of things, I would love to like physically not be in, but be in the location of a supermassive black hole and see the accretion disk with my own eyes and like just see what that space really looks like. We got the one amazing image last year, but I want to be there in person. And then the other one is to like perform on Broadway, which is just about the same level of impossible. So,
I mean, if you
We would
had
all be super old.
teleportation, you could
You'd be able
perform
to
very briefly.
Yeah.
dragged off stage.
We would all be super old when you come back, Alexander.
Yeah, that would be a bummer. We'll just take everyone with us. We can just orbit around a supermassive black hole. All right. Thank you so much to all of our panelists for coming on and talking about who you are and what you do and what you're interested in. I really appreciate it. I know the folks out there really appreciate it. That is our show for tonight. Aaron and I have been talking. There were a lot of great questions in the chat, specifically about aurorae that we didn't have time to get to. So Aaron is going to throw his email out there so that any of you folks can contact him to ask him about this topic that he knows quite a bit about and far more than me. But that is, in fact, all we have for the evening. So again, thank you to our wonderful panelists. Thank you to Aaron. And thank you to all of you for coming and watching us tonight.
Alex, can I add just one note? Is that
yes.
those folks that are interested in Aurora, Bob Lysak will be giving a Minnesota public lecture this fall. And you can go to our same website to find out the date and the time. But he'll have a lot more to say about Aurora and a lot more time to answer these questions.
Yep, absolutely.
And he'll say it right.
Thank you for that plug. And now, without further ado, have a wonderful evening, everyone. While I figure out how to stop the live stream. There we go.